Have you ever wondered how a GPS system calculates the fastest way to get you somewhere? Perhaps the grocery store, or perhaps our small school in Kentucky, Berea College. Point A to B, pretty simple, right? But wait, what if you want to hit multiple places along the way? Does the order matter? Yes, it does. When you have multiple destinations, it's all about efficiency. To figure this, we can imagine the world as a bunch of points, places we can go, connected by lines which are the paths between them. Some paths are short, some are long. The goal? Find the path that takes the shortest time without wasting miles. And that's where Dijkstra's algorithm comes in. Instead of just picking the closest place at each step, it looks at all possible paths from your starting point and makes decisions based on the overall cost for each potential next step. It always chooses the next location by determining which would lead to the shortest total distance, not just which is closer. And it updates the map as it goes. Step by step, it builds the shortest possible path to every point. And it's not just theory. Dijkstra's algorithm is used every day to power GPS systems, delivery apps, flight planning, and even to control network traffic. Now imagine this. After working your soul-sucking corporate software engineering job 15 hours a day for 12 months, you get fired by Elon Musk. Congrats, this is a perfect time for a vacation. You decide to visit 4 cities: New York, Miami, Austin, and San Francisco. But there's a problem. If you fly to them in a random order, you'll waste a ridiculous amount of time and fuel. Instead, you can use Dijkstra's algorithm to map out the most efficient path. Let's imagine that we're starting our trip across the US in Austin. Our goal is to visit New York City, Miami, and San Francisco in an order that helps us achieve the shortest total time. We can think of each city as a node, a point on the graph, and each flight between cities as an edge, a path on the graph. The numbers next to the flight paths are the times it takes to travel, the weight of each edge. We start our journey in Austin. Our goal is to find the shortest path to visit New York City, Miami, and San Francisco. From Austin, we have 2 options. Fly to New York City in 4 hours and 15 minutes, or fly to San Francisco in 3 hours and 35 minutes. We will first pick the next closest unvisited city from the starting point, which is San Francisco. Then from San Francisco, we choose the closest unvisited city as well, Miami. So far, we've traveled 9 hours and 5 minutes. Dijkstra's algorithm will go back and try paths we have not yet tried in search of the most efficient path. So we start again from the beginning, and we choose our other option, New York City. Then from New York City, we choose the closest unvisited city again, and we end up in Miami just like in the first calculation. Now we can stop and compare times. In this second calculation, we have traveled 7 hours and 15 minutes. So now we know that New York City and Miami are the most efficient first 2 steps, and we know that the last step must be San Francisco, as it is the only option left. Our total travel time is 12 hours and 45 minutes. Just like that, Dijkstra's algorithm gets us there in the fastest time, 1 smart step at a time. It is a great example of how much of a difference efficiency can make while planning. Thank you for watching.